Thank you. So I'm going to talk very briefly about reasoning about types in code, which is based on a book I'm writing right now. And the main goal of the book is to describe what are the pieces of theoretical knowledge that functional programmers need in order to be able to reason about their code. Reasoning about code is something that we often hear. A programmer is supposed to be reasoning about code. But what does it actually mean? Everybody is reasoning about everything. So I would like to describe that functional programmers have specific ways of reasoning that are not available to other programmers. And these are very specific techniques that functional programmers can learn, or should learn, maybe, in order to be effective. And these are specific kinds of reasoning about types and about code. And examples of this reasoning are that a programmer can design a data type or derive equivalence between types in order to simplify a given data type into an equivalent another type. Or programmers can use type constructions, for instance, type product and co-product and so on, in order to create data types that have properties they need. And as for reasoning about code, the main example of this reasoning is finding whether code satisfies certain laws. For instance, laws of a monad need to be verified. The programmer needs to implement a certain type class with functions that satisfy these laws. And in order to check that they do, the programmer performs specific kinds of mathematical reasoning. Or the programmer checks that certain functions are equivalent. They compute the same thing. And so you can even derive sometimes a simpler code that is equivalent. And very importantly, this reasoning is completely mathematical. It is rigorous, and it is not just some trial and error. These are actual mathematical proofs that can be made quite rigorous. The amount of mathematical knowledge that you need to be able to do these things is quite limited, and certainly not at graduate level, at most at the beginner and undergraduate level, or even high school mathematics. For instance, it is similar in complexity to manipulating polynomials symbolically, or multiplying, say, elements in a monoid, which are not commutative, but it's a very simple kind of calculation. Now, this is my proposed book that I'm writing. I have 8 chapters by now. We just had a very interesting talk about how not to pitch your book. I did take notes from that talk, and I can do everything wrong about pitching this book. I don't know who is the manager for the functional programming theory division at O'Reilly. There's no analog for this book. It's unique. There's nothing on the market that's similar in any way. I'm completely settled on the title. There's no discussion about the title. But at the same time, I have no data to show that the publisher will benefit. And the audience for the book probably is very small, and I'm going to have over 700 pages. So I basically crossed all the don'ts in pitching this book. This book will explain what are the techniques of reasoning that are available. I will also derive everything symbolically. I will derive the laws, and I will give motivations for these laws that start from real-life programmer questions about code. So my motivation is not coming from theory. It comes from code. This is the main approach that I'm taking with this book. So here are examples of reasoning tasks that programmers might need to do. Given a value of type either of z and r to a, or r to either za, can we compute the value of the other type? So here are two functions, f and g, with these type signatures. Can you implement these functions? It turns out that you cannot implement the function f, but you can implement the function g. So the function f, for some reason, cannot be implemented, but the function g can. So here's the code for g. The code is very simple. So why can't you write something simple also for f? It is not obvious that f cannot be implemented. You need to reason about it. And the reasoning is an example of what you need to do. I'm not going to go through it right now, but the technique of reasoning that will explain to you why f cannot be implemented but g can, or the intuition behind it. As an engineer, you don't necessarily have to derive from first principles, from axioms, but you need to understand what is correct and have intuition about it. Another example is that I am writing code where I have a future and I have an either at the same time. I would like to have them at the same time. I actually cannot. This is not going to compile in Scala because the for yield block cannot have different types if they are not subtypes of the same type. But I would like to combine them. So how would I combine them? And if I don't combine them, my code is going to be ugly. And actually, this kind of situation happens frequently. And the programmer needs to know that you can combine like maybe like this or like this. The programmer needs to know that only one of them is correct. That this way is correct to combine these two types, but this one is not correct. So why is it not correct? So this, again, is a mathematical statement that can be proved rigorously. And the reason is that you cannot implement flat map correctly for this type. But you can implement flat map for this type. Proving that you can or cannot implement flat map with the correct laws is an example of a mathematical proof that a programmer at least should have seen at some point, if not able to do all the time, not necessary to do all the time, but the programmer should recognize that this situation has a mathematical reason to exist, and so that this is the right solution. And it's not just an opinion that it's the right solution. It's actually a proof that you can do. Another example is, for instance, I can imagine a business logic that tells me my data type must be like this, and I would like to implement flat map for this. Can I do that? The answer is no. You cannot implement flat map for this type. In fact, you can implement the type signature, but it will fail the laws. You need to understand that. This is not trivial, not obvious, and again, this is an example of reasoning that you can do as a functional programmer. Let me skip a little and go through some notations that I have developed for my book. It turns out that you need to do a lot of computation symbolically with types and with code. it is very long and difficult to do these computations if you use the syntax of your programming language. It will be very hard to understand where the proof is going. And so what we do is we develop special notation that is shorter. And in this table, I show the notation for types. The tuple, for instance, is denoted as a product, and the either is denoted as a sum, and the unit type is denoted like this. And type constructors with type parameters are denoted in this way, where type parameters are superscripts. So then, for example, this Scala code corresponds to this notation. So PA is the type constructor with type parameter A, and the superscript is used for type parameters. And this is a sign which means equals by definition. And this is then the unit part of the option and the product of three A's. And similarly, a function with a type parameter would be denoted like this, for example. And this seems to be a convenient notation, because you can then show equivalence of types, examples I'm showing below, where this type is equivalent to this type. And this is very similar to polynomials in school algebra. Equivalences with function types are not similar to algebra in this notation, but sometimes people use exponential notation for this, but I found it to be extremely inconvenient in calculations, because you have always a lot of arrows that are nested, and exponential notations become very, very difficult to use. So you need to get used to this notation. And I have a similar notation for code in order to reason about properties of functions. So for example, composition of functions I denote like this, where the semicolon symbol denotes the forward composition, which in Scala is like this. A forward composition has small advantages over the backward composition that is usually denoted by the dot. One advantage is that it's easier to check types. If you type the first function a to b and the second b to c, then it's obvious what this composition is doing. And it turns out to be also very convenient to use the pipe symbol, or this triangle. In some languages, you actually have the triangle operator for this. In Scala, it is pipe, which substitutes arguments into functions that are on the right. So it turns out that a lot of Scala code looks like this: x dot something dot something dot something dot map dot flat map dot filter. And these are functions into which you substitute an argument from the left. And so reasoning about these functions using this triangle notation turns out to be extremely convenient, and also very well adapted to reasoning with the forward composition. So people who are familiar with this kind of reasoning have usually seen it in the backward composition without the triangle operator. Turns out that it's equivalent, but it's a little easier to follow. So I have these notations, and with these notations, I would like to show you very quickly examples of what can be done through reasoning. Now, in my book, I will explain this in full detail, but here I will just zoom very quickly through the results. So the free monad has become popular in the Scala community around 2015. And however, it was not very clear, so people tried to give talks about it to explain to each other what it was. And so if you take one of these talks from Gabriel Gonzalez, which was in Haskell, and you translated it into Scala, then you get this code for the free monad. And then the talk by Runar Bjarnason 2 years later was in Scala, and it showed this code. And then 2 years later still, a talk by Kelly Robinson showed this code. And they all were talking about the same free monad. So then a programmer asks, are these definitions different, or are these definitions equivalent? And how to reason about them. What is it that I should use? Should I use this code, or that code? Reasoning about this is not easy if you use the syntax of the language. So the first thing I do is I rewrite these in the type notation. So for example, the definition in the first talk looks like this. And the definition in the second talk looks like this. Now you see there's an existential quantifier in the second definition, but it wasn't in the first definition. Certainly it's not easy to see from the code that you are actually using an existentially quantified type. The type parameter A in this code has a very different role from the type parameter T, because the trait you're extending does not contain the type parameter A. And so in order to create a value of this case class, you have to choose the type A somehow. So this creates an existentially quantified type. But this is not easy to see immediately from the code. And reasoning about this is not easy, unless you write it in a notation that makes it very clear that you're using an existential quantifier. And so with this, you write another formula. Instead of 3 case classes, I have 3 parts of the sum, so to speak. And then I can reason about them and show that they're equivalent. So the definitions 1 and 2, I'm just going to go very quickly through this, can be shown to be equivalent if the type constructor f is a functor. And to do that, you need a property which is called a Unida identity. A Unida identity is this property, which is for any functor f. Now this you need to show that this is true. This is not obvious. But this can be shown using code, that you can write functions that transform one to the other, and they are inverses of each other. In other words, you cannot see that these functions will ever give you different results. So this you learn as part of studying the theory of functional programming. So this is, of course, an advanced example, but it is an example of the specific kind of reasoning that is available when you use functional programming, and it is not available for other paradigms of programming. And definitions 2 and 3 are equivalent if you use monad laws. Now this, I'm not going to explain all steps in this derivation, but this is how much you have to write, and you would write that on paper and reason about it as you write to show that these definitions are equivalent. You take the first definition, you transform it, and eventually you arrive at the second definition. So this is about as complicated as dealing with some polynomials, expanding the brackets, rearranging the sums and the products. So this level of complexity is about the same as in the school level algebra. Now I would like to conclude with a more advanced example where I will go very quickly and not at all explain how this was derived. And the example is the so-called selection monad. Now this is not a very well-known monad, but there was a paper that tried to derive the transformer for the selection monad like this. And the author of the paper writes that they tried to prove that this transformer satisfies the laws of the monad, but they could not prove it, neither with a computer program nor by hand. And the proof was too hard, I'm guessing, because they tried to do this proof by Haskell syntax. And that is not good enough to have proofs of such complexity. you write down a program in a Haskell syntax, you have no idea how to transform it because the notation does not help you. So I developed code notation that specifically helps me to understand where these proofs are going and how to find them. Computers don't help you here so much. A formally verified proof usually requires you to know in advance how to do the proof by hand. Automatic tools cannot find a proof for this because this statement depends on an arbitrary monad M, about which you know nothing except that it satisfies the monad laws. And usually computer programs cannot find proofs in such a general way. So in the code notation that I developed, the proof only takes 5 lines of calculations. And I'm going to show you these 5 lines. This is a definition of the Kleisli product in the new monad, and these are the 5 lines. Now, these lines might appear to be long, but they're straightforward. You're just writing out an expression, you're substituting into it a little simplification, and you're done. So this line and this line are equal symbol by symbol. And this shows the associativity law for the new monad. This is the associativity law that the author of that paper was not able to derive, either by computer program or by hand. I believe because they haven't spent time to develop adequate notation that helps to see where the proof might go. This is, in my view, the techniques that are advanced but quite possible for functional programmers to master. Maybe about some months of learning, but once you have gone through this, you will be much more effective in all kinds of reasoning tasks. So in my book, I have everything online, the entire source code of the book. It is distributed under the GNU license, so free to download in the sense of the Free Software Foundation. Please take a look and let me know what you think. Thank you. All right. Any questions? All right. If there are no questions, thank you again.